The first way to detect the problem of autocorrelation is by the graphical method. We can plot UT, the error term, with time, and also UT with the previous error term UT minus 1. So if we plot between UT and UT minus 1, we can clearly see that this is a positively correlated and this is a negatively correlated. So here we have a positive autocorrelation and here we have a negative autocorrelation. But when we plot UT against time, okay, so as time increases, so you see that uh, the, the error term, okay, from if the error term, if rho is positive, if rho is positive, then if error term in the previous year is a positive value, then the error term in this period will also be a positive value. So it will extend to some period of time that it shows a positively correlated between previous year's error term and the existing period error term. But then if the error term is negative and then if rho is positive, then we're going to have a negative also error term in the existing period. So meaning that if previous year's error term is negative, this period error term is also will be negative values. So this same direction of sign, previous year positive, this year positive, previous year's negative, existing period negative, shows a positively correlated between the error terms. But when you see a negatively correlated, meaning rho is a negative values, so if previous years is a positive value, then this year will be a negative value. If this year is a negative value, then next year error term is a positive value. So it flips between times. So suppose we have starting of 1980, so 1980 suppose is a positive error term, 81 negative, 82 positive, 83 negative, and so on. So this flipping shows the negative relationship uh, between the error terms. So this shows a negative autocorrelation. So you have to understand that the axis is different. This one is plotting UT against time. This is UT against UT minus 1. For the formal method of detecting autocorrelation, we will discuss two tests. The first one will be the Durbin-Watson D test, and the second one will be BG test. So both tests is a statistical test, meaning that the structure of a statistical test is just the same. You need to have the H null and H1, you need to have the alpha level, you need to have the test statistic, you need to have the critical value, and you need to make the decision. So for detecting autocorrelation using statistical test, your H null would be no autocorrelation, and your H1 or alternative hypothesis will be there exists autocorrelation. So for the test statistic, we will use the Durbin-Watson D statistic. So this is the formula, and what is nice about this D statistic, it is usually automatic given in the regression analysis. So once you use eViews or SPSS or Stata, when you run the regression, you will always get directly the Durbin-Watson D statistic. So this is the test statistic. So this test statistic we need to compare with the critical value from the Durbin-Watson table, and then we need to decide whether reject or do not reject H null. Before we go into the hypothesis testing, we need to understand the assumptions when using Durbin-Watson. So first is that the regression model needs to include the intercept term. So if the model does not have any intercept term, meaning it is the model through origin, then we cannot use the Durbin-Watson test. And the explanatory variables or X are non-stochastic, which is fixed in repeated sampling. The disturbance, the UT, is following the AR1 scheme, which is UT equals to rho ut minus 1 plus epsilon t. Assume that ut is normally distributed, and also the regression model that cannot include the lag values of the dependent variable. So example here, this is an autoregressive model. So our dependent variable is yt, but then one of the independent variables is yt minus 1. So this is the lag of the dependent variable. It becomes the one of the independent variables. So this is autoregressive model. So you cannot use the Durbin-Watson for this kind of model. And also the last one, there is no missing observation in the data. If we expand the Durbin-Watson test statistic, we will get this. And then if we equate the summation of ut minus 1 hat squared is approximately equals to summation of ut hat squared, then we will simplify this formula into this. And if we define this term as equals to the rho hat, and then we will get d is approximately equals to 2 times 1 minus rho hat. So since rho is between minus 1 and 1, so if we take the end of it, example minus 1. So if this is minus 1, then 2, 1 minus 1 will be 2 times 2 will be 4. And then if we take the extreme, rho equals to 1, then 1 minus 1 will be 0, and 0 times 2 will be 0. So meaning that the D test statistic Durbin-Watson will be between 0 and 4. It will be, there's no values lesser than 0. There will be no values which is larger than 4. And meaning that the estimated D value must lie within these limits. We can construct this Durbin-Watson D statistic, whereby we now understand that D statistic will be between 0, the lowest value, and also the highest value will be 4. So it will be between 0 and 4, and then in the middle will be 2. So we can divide the region between 0, DL. DL is the lower limit, DU is the upper limit. This is 4 minus du, and this is 4 minus dl. Okay, so if it is between this du and 4 minus du, this region, this means do not reject H null. So if it falls in this region between 0 and dl, this means that there is evidence for positive autocorrelation. And if it falls in this region, then there is evidence of negative autocorrelation. And if it falls between dl and du, then this is zone of indecision. You cannot decide whether it is positive or negative autocorrelation. And also here we cannot decide indecisive, meaning we cannot decide whether it's a positive or negative autocorrelation. So we can get the value of dl and du from the table. So once we have dl and du, we can always construct, find what is 4 minus du and what is 4 minus dl. So this is an example of the EViews output. Once you regress the dependent variable on L and U, you have that all this estimation, and you see here this is Durbin-Watson stats. So this Durbin-Watson stats is the test statistic for the Durbin-Watson test, which is 0.910767. So this is already calculated. This is the test statistic for the test. So once you have the test statistic, in any hypothesis testing, you need to compare with the critical value. So for finding the critical value for Durbin-Watson test, we need to know the alpha. So suppose you are using alpha is 5% and you have this K prime. So what is K prime? K prime is the number of independent excluding the intercept. So basically K prime is just the number of regressors. So here in the model there's only one independent, so meaning that K prime equals to 1, and also we are using sample size n equals to 24. So referring to the table of Durbin-Watson, okay, so this is the critical values. So for Durbin-Watson, we need to use the K prime and also the sample size. So K prime, the number of regressors is 1 and n equals to 24. So if you look from the table, we get the DL here is the lower limit, which is 1.273, and also the upper limit is 1.446. And this is the table for 5% level of significance. So you have H null, there's no autocorrelation, H1 autocorrelation exists. So this is the line that we need to construct from 0 to 4. In the middle is 2, and then we have this lower limit and upper limit. So we found from the table lower limit is 1.27 and here is 1.45. So this is the critical value. So what we need to do is we need to compare the test statistic with the critical value. So this test statistic falls at this region, which is between 0 and 1.27. Therefore, since this is the rejection region, we can reject H null. So when we reject H null, we are saying that autocorrelation exists. And for this, we know that it's going to be a positive autocorrelation. So this is the line just now between 0 and 4. So we have, this is the area, the region for positive autocorrelation. This is the region for negative autocorrelation. And if it falls between this and this, then we have do not reject H null. From the Durbin-Watson d-test, we have the modified d-test. So there are people suggesting this modified d-test, whereby we simply can say whether it is a positive autocorrelation or negative autocorrelation. In modified d-test, this area is now positive autocorrelation. In modified d-test, this area now becomes the negative autocorrelation region. So in the exercise, if you are using the Durbin-Watson d-test, then you are applying to this structure, whereby you have the positive autocorrelation, indecision, no acceptance region, indecision, and also negative autocorrelation. But if you are using following the Durbin, the modified d-test, then here will be a positive autocorrelated, and then this one will be a negative autocorrelated.